In the last lecture, we have studied about the combination logics. What are the combination logic? And we discussed that a combination logic has n number of inputs and m number of outputs. There are two ways of discussing an combination logic. The one first is the analysis, and the second one is the design. So we have done an example of the analysis. In the analysis process, we are given a schematic or a circuit, and we have to find out its Boolean expression for the output, and we have to construct the truth table. On the other hand, when we have to design a combination circuit, we are given some specifications, out of which specifications, first of all, we have to find out number of inputs, number of outputs. Their relationship between input and output is given in the specifications, and as per the specifications, we make truth table. We solve the truth table to find the optimal SOP or POS term. Then we implement the circuit with the help of the basic gates. We also discussed some example like BCD to XS3 codes. So the input is 4 input BCD, output will be a 4-bit XS3. We have discussed half adder, which adds 2 bits. We have discussed full adder, which adds 3 bits. Now in today's lecture, we are going to discuss about the subtractors, how the subtraction takes place, and how we have to design a subtractor. As in case of the adder, again subtractors are of 2 types, half subtractor and the full subtractor. In the half subtractor, as in case of the half adder, it subtracts 2 bits, and a full subtractor subtracts 3 bits. Now let us discuss in detail. First, we are going to discuss the half subtractor, and the process of the subtraction is it produces output x minus y, where x and y are both inputs, and it will produce 2 output. First is the difference, another one is a borrow. Now the difference is the case when we subtract 1 minus 0, then the difference will be 1, 0 minus 0, difference will be 0, 1 minus 1, difference will be 0. But when we subtract 1 from 0, 0 minus 1, so it is not possible, and in that case we have to take a borrow when we are subtracting 0, when we are subtracting 1 from the 0. Now that will be pretty much easier when we look into the truth table. So as far as the specifications are given, that we have to design a half subtractor. Here I have written HS in the block diagram. It has 2 input x and y. Process is x minus y, and we have 2 outputs, D for difference, B for borrow. So here is the truth table with the 2 inputs x and y. We have 4 combinations, and the combinations are defined as 2 raised to the power 2, that is 4. Sorry, ranging from 0, 0, 0, 1, 1, 0 and 1, 1. So you can just look into the table and find out the way how the outputs are listed in the table. For the first case, when we subtract, for the first case, when we subtract 0 minus 0, so difference is 0 and we need not to take any borrow. I left for the simplicity the second row. I come to the when we are subtracting 1 minus 0, then the difference will be 0. Borrow will be, difference will be 1 and borrow will be 0. Again, when we are subtracting 1 minus 1, then there is no borrow and 1 minus 1 is 0. Now consider the case when we are going to discuss 0 minus 1. So it is not possible to subtract a 1 from a 0. Then what we have to do, we have to take a borrow. When we take a borrow, now the borrow is 1. Now this 0 becomes 1 0. So 1 0 is 2. 2 minus 1 is 1. So when we are subtracting 1 from the 0, then borrow is 1 and the difference is 1. So this is the way how this truth table has been obtained. When we find out the Boolean expression for the borrow and the difference, here borrow has a combination 0 1, that means x bar y. Difference has two ones, and the expression will be x bar y and x y bar. You can do it with the help of the K map, or directly you can find out the expression, and the expression comes d equals to x bar y plus x y bar, that is equals to sum as a case of half adder, and b equals to x bar y. So I have drawn a circuit here where A, B are input just like X and Y. D is the difference that is obtained with the help of an XOR gate, X bar Y plus X bar Y bar, or A bar B plus AB bar. And Boro is A bar B or X bar Y. So here B out denotes the Boro output. Similarly, we can construct a full adder, a full subtractor, and the operation will be x minus y minus z. So z is the previous Boro. So when we'll draw the truth table, then it will be much easier how this operation is obtained. What we do, we first subtract y minus y minus x. We subtract y from x, then whatever the result, z is subtracted from that particular result. So here input will be 3, x, y and z, output will be 2, Boro and difference. So let us discuss here. X, y, z, 3 are inputs. With 3 inputs we have 8 combinations from 0, 0, 0 to 1.
सर आपने
आपकी वॉइस लैग हो रही है सर बहुत।
सर आपने तो पीछे बताया सर, उसमें आवाज ही नहीं आई, कुछ भी समझ नहीं आया
सर। आवाज नहीं,
तो अभी आ रही है आवाज? नहीं आ रही है? अभी आवाज आ रही है? नहीं, जैसे 5 मिनट आवाज आ रही है, अभी नहीं आ रही है?
सर अभी भी
जस्ट अ मोमेंट। For the half subtractor, operation will be x minus y. So it produces x minus y, and the output will be difference and Boro. So with the specifications, we can draw the block diagram. Block diagram has 2 inputs x and y, 2 output Boro and difference. In the truth table, we can see with the 2 inputs, we have 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1, and we have to produce an output in such a way that the output is x minus y. So for the first case, when 0 minus 0, difference will be 0, and we need not to take any Boro. So the Boro is 0 and difference is 0. When we do 0 minus 1, so it is not possible to subtract a 1 from the 0, then we have to take a Boro, then this x becomes 1, 0. So 1, 0 is nothing but 2. So 2 minus 1 is 1, and we already have taken a Boro, that means Boro is 1. 1 minus 0, difference is 1, Boro is 0. 1 minus 1, difference is 0, Boro is 0. So with this particular truth table, we can find out the expression for difference and Boro. So difference is x bar y plus x y bar, that can directly be derived where there is a SOP term. Here it is x bar y or x y bar, and Boro is nothing but x bar y. So here in this way we can draw the circuit. Here you can also write x and y. So the difference is x XOR y, and the Boro is x bar y. So this is the way the circuit is almost similar to what we have obtained for the half adder. Now when we move to the full subtractor, full subtractor does the operation x minus y, and whatever is the result, then z is subtracted from that particular result. So we can draw the truth table for the full subtractor. Here we have 3 inputs x, y and z. With the 3 inputs, we have 8 different combinations ranging from 0, 0, 0 to 1, 1, 1, as we have discussed earlier. So output again will be 2. One is the Boro, another one is difference. So please be attentive. Then otherwise it will be very difficult that how this truth table is derived. I'll discuss each and every case. So when I subtract 0 minus 0, so sum is 0, difference is 0. Then in the difference is 0. So 0 minus 0 again, difference is 0, borrow is 0. So the first case 0 minus 0 minus 0. The operation will be like this. Now 0 minus 0, difference is 0, borrow is 0. Again when we subtract 0 minus 1, so we have to take a borrow. So the borrow is 1. Now 2, this y becomes 1 minus 1 0, 2. 2 minus 1 is 1. So in this case difference is 1, borrow is 1. Again 0 minus 1. So 0 minus 1 not possible. We have to take a borrow. So the borrow is here 1. Now it becomes 2. 2 minus 1 is 1. Then 1 minus 0 is 1. So difference is 1. Borrow is 1. Again 0 minus 1. We have to take a borrow. So the borrow is 1. So 2 minus 1 is 1. Then 1 minus 1 is 0. Sorry. Then 1 minus 0 is 1. Borrow 0. Then 1 minus 0 is again 1. So borrow is 1. Difference is 0. 1 minus 0, 1. 1 minus 1 is 0. So difference is 0, borrow is 0. 1 minus 1 is 0. 0 minus 0 is 0. Difference 0, borrow 0. 1 minus 1 is 0. Then 0 minus 1, we have to take a borrow. So we have taken a borrow. Now this becomes 2. 2 minus 1 is 1. So this is our truth table and we have to solve the two K maps, one for D and another one for B. So with the help of the truth table, with the help of the K map, we find out the expression for difference comes to be X XOR Y XOR Z. That is again equals to the sum of the full adder, and borrow comes to be X bar Y plus X bar Z plus YZ. So it is exactly equals to the carry as in the full adder, except that X is inverted or X is replaced by XZ. So you can do it with yourself. Draw the truth table, draw the K map for one for B and one for D, and you will find out that the difference and borrow will come in such a way. Now we can do the schematic as in case of the full adder with the help of half adder. We have drawn here full subtractor with the help of half subtractor. So this is one is your first half subtractor. This one is your another half subtractor, and we have ORed the both carry or the both borrow out. So in such a way we can implement a full subtractor. Then it must be kept in mind. Then whenever there will be a question for designing a adder or subtractor, there are the 99% chances that you will get a question regarding the adder, because as we have discussed in case of when we are studying two's complement or one's complement, then there is no need to design a subtractor, because the subtraction process can be done with the help of the two's and one's complement. We just have to add the number and we need not to subtract the number. So it is just for the simplicity that we are discussing here the half subtractor and the full subtractor, but the process of subtraction is done with the help of the addition, and that addition is done either with the help of two's complement or the one's complement. So so far what we have discussed, we are discussing the half subtractor or the full subtractor, half adder, full adder, which were adding the number of bits. But when we are doing the addition process in our computer, that the minimum computer which you are using nowadays, it will be either 32-bit or a 64-bit. So we can say that we have to add two number A or B, where A is of 32-bit and B is of 32-bit, like this. So we have to, if we have to add two numbers, then we have to add 32 bits parallelly. That's why the parallel adder comes into the place. And in the current scenario, whatever you are purchasing, your either mobile or your computer, it is almost each and every laptop or computer or processor is of 64-bit at least. So with the 64-bit processor means that your adder in the processor is of 64-bit. So the parallel adder comes into place when we have to add two numbers with n number of bits. So this is the process, because till now, as far as our knowledge is concerned, yeah, or what we have studied so far, that half adder adds 2 bits, full adder adds 3 bits. So let us discuss how the process is done for the parallel addition. Now often we must add two n bit numbers and a carry, because when we are adding a number there will always be a carry. So we are interested to add two numbers with n bits. So here n depends upon the size of your processor. If your processor is of 32 bit, then you are adding two 32 bit numbers. If the size of your processor is kept for 64 bit, then you are adding two 64 bit numbers. So suppose let us take an example that I have two numbers A and B. Here A is of 4 bit, A0, A1, A2, A3. B is of 4 bit. Sorry, this is it should be B0. B0, B1, B2, B3. So I have to add two numbers A and B, and how it will be added? Suppose initial carry is 0. I will add A0 plus B0, then it will produce a sum 0 and it will generate a carry. Then carry will be forwarded to the next bit. Then again I will add C1, A1 and B1. It will produce a sum S1 and a carry will be generated that will be forwarded to the next bit. Then I add C2, A2, B2. It will result sum S2. The carry will be forwarded C3. Then I add C3, B3, A3. It will produce sum S3 and the carry will be forwarded. Now, if it is just a 4-bit number, then this is known as carry out, because if we have n bit number, then the sum will be of n bit and there will be a 1 bit of the output. Here C0 is the input carry, which is the initial carry, which we always assume in the mathematics that initial carry is 0. So we assume that the initial carry is 0. This is what happens when you are adding two numbers on your with your paper pen. So in that case, when you are using computer, the same mechanism we have to develop, that how to add two n-bit numbers. And the mathematics behind this is that for the classical approach, the input is 2n plus 1. So this is n, 4 plus 4, 8 plus 1 is the input carry. So input is in this case 9 bit and the output is of n plus 1. So n bit output sum and 1 bit is carry. So we have to design a n plus 1 output, two level example SOP design, what we have done so far. But the problem with that approach is that too many gates are required, fan-in is too large and not practical when n increases greater than 3. So in that case, we need to develop a hierarchy or an algorithm so that or an approach so that we can design this adder circuit easily without any much more mathematical complexity. So let us discuss again here. So we use iterative circuit which reduces the complexity of the overall design. Now suppose take the same example and we are going to develop a block diagram for the same circuit. We have two numbers of 4-bit A, B. We have to produce sum of 4-bit, carry of 1 bit, and C0 is your input carry. Now what happens? This is our design. In this case, I may use four full adders. First full adder adds A0, B0, A0, B0. Sorry. C0 input carry, which is initially 0. When this adder will produce, it will produce a sum and a carry. That carry will be carry forwarded to the next bit. In the next bit, we are adding A1, B1. So A1, B1, input is C1. It will produce sum 1. Next carry will be forwarded to the next bit. Next bit will add A2, B2, produce sum S2, and next carry. And in this way, the carry is propagated from one bit to the another bit. And if you have a 64-bit processor, then in such a way, we have to use 64 full adders to produce a 64-bit sum and a 1 bit of output. So this is the approach how we can add two numbers A and B of n bit in a parallel mode. Now the complexity of the overall circuit is reduced. We need not to solve any K-map. We need not to solve solve any truth table, we just have to simply put up if it is 64-bit, then 64 full adders. If it is a 4-bit, then 4-bit full adder. In such a way, we can find out a parallel adder. So here the complexity has been reduced. For n equals to 4, inputs are 9, outputs are 5, and two power pins, one for VCC, another one is for ground, and we can get a 4-bit adder is accommodated in a 16-bit package. Otherwise, when we are solving it with the help of K-map, it will be a very large process and we need a very large hardware. So to add a 4-bit number, we can get a 16-bit IC in the market, and with which we have in which we have 9 inputs and 5 outputs and 2 power pins. So this is how the complexity has been reduced when we are using parallel adder to add 4-bit numbers. Now the carry look ahead adder, the problem with the previous parallel adder, let us discuss in detail. Suppose this is your one full adder, what we have used. We have used 4 such full adders. So I am just talking about this full adder, that how this full adder will work. Till now we do not have discussed anything about delay. Anything about delay time, how is the gate delay, how is the wire delay. So we are taking that the circuit is static whenever we are giving input, at the same time we are getting output. But when we go at the frequency of, in your processor you are getting a frequency of 3 gigahertz, that means it takes 1/3, that means 0.33 nanosecond to execute an instruction. So if we think about at that time, or at the time scale of nanosecond, then there is always a delay in the circuit. So we are going to discuss in the fast adder, that is a carry look ahead adder, what the delay means. Suppose this is your circuit of the full adder, which we are using to construct a parallel adder. Here the output of the first XOR gate, I have indicated it P of I, that is carry propagate. Here output of the first AND gate, I have written here or given the node as GI, carry generate. Now this output of this gate will be PI XOR CI. CI comes with the input, carry input, and here CI plus 1, that is the next carry will be PI CI. It comes PI CI or GI, and that is the CI plus 1, that is the next carry. So what happens? Let us discuss mathematically. Now fewer gates than 2-level implementation have significantly slower ripple effects of carry. Suppose if we look into this circuit, this is level 1, this is level 2, and this is level 3. Now suppose each level has, or we can say sorry, if each gate has a propagation delay of 1 nanosecond, suppose, means when we give an input and it take 1 nanosecond to give the output, and that is pretty much easier and pretty much general, that every gate has its delay in the response. Now suppose with the 3 level, the first level is here 1 nanosecond, then 1 nanosecond, then 1 nanosecond, means sum will be generated after 2 nanosecond and the carry will be generated after 3 nanosecond. So this is the issue with the parallel adder, means sum will be generated at after 2 nanosecond and the carry will be generated after 3 nanosecond. And if I look into this circuit, means whenever A0 and B0 are given, because all the inputs will be given simultaneously, A0, A1, A2, A3, B0, B1, B2, B3, all will be given simultaneously, and then the sum will be given after 2 nanosecond and this carry will be generated after 3 nanosecond. But initially this A1 and B1 are already there, so the value will be, initial carry is 0, it will produce sum exactly according to the input carry and the input, but after 3 nanosecond there will be carry. That means after 3 nanosecond S1 will again change. So the output of this particular 3 nanosecond C1 will be generated after 3 nanosecond and C2 will be generated after again 3 nanosecond. So it will take 6 nanosecond to generate C2, and it will take 9 nanosecond to generate C3, and it will take 12 nanosecond to generate C4. So there is a delay, continuous delay for generating the carry, and this is because sum is generated after 2 nanosecond and carry is generated after 3 nanosecond when we are implementing the parallel adder with the help of the full adder. That's why there is a need to construct a circuit which acts fast and which produces carry and sum at the same level. So here the sum is generated after 2 gate delay, so we have to find out a way that the carry also generates after a 2 gate delay. So this is the purpose here, that we have to optimize the design so that carry and sum generate exactly after the same gate delay. Now for an n-bit adder, propagation delay is equals to 2 into average gate delay into number of bits, or equals to 2n into d, where d is the average gate delay. What we have done here, average gate delay, if we have taken 1 nanosecond. Now we have another design, that is the carry look ahead logic, and we define Pi equals to AI XOR BI. Here Pi equals to AI XOR BI and GI is AI and BI. So with the same design we have put it the numerical value. Pi is AI XOR BI and GI is AI XOR AI and BI. And now sum is AI XOR BI XOR CI. You can look here. Sum is AI XOR BI comes from here, XOR CI, that is your SI, and CI is PI CI or GI. So these are the numerical values or the Boolean functions which we have put at the output of the gate, and we have to evaluate each for the each level. So CI plus 1 is GI or CI PI. So we put these value with the n number of full adders. We have A0, full adder 0, full adder 1, full adder 2, full adder 3. So the observations are that all carries be generated simultaneously. If we put the value 0, 1, 2, 3 here, because the problem is with the carry, because carry is taking 3 gate delay. So I put here, if I equals to 0, then the C1 will be G0, C0, P0, that will be C1. C2 will be, if put I equals to 1, then the C2 will be G1 plus C1, P1, and we can put the value of C1 from the previous value. Now in this case, we get C2 equals to G1 plus P1 C1, C3 equals to G2 plus P2 C2. Now the value of C2 will be accomplished from the C2 here. We get G2 plus P2 G1 plus P2 P1 C1. For the C3, I equals to 3, we have G3 plus P3 C3, and we can put the value of C3 here, and it will be G3 plus P3 G2 plus P3 P2 G1 plus P3 P2 P1 and C1. So in this way, the delay for some P and G is 2 gate delay. For carry, it takes 2 gate delay, and for the XOR, it again takes 2 gate delay. So the gate delay is equalized, and at the same time, we are getting carry and sum, and the total gate delay will be 2 plus 2, 4. So after 4 gate delay, each and every sum will be there, and each and every carry will be there in the circuit. So this is what we have generated: C1, C2, C3. We are given C0, P0, C1, C0, G0, P0, G1, P1, G2, P2. These are the values which we have implemented with the getter. So first gate delay is here, second gate delay is here. Means exactly we are getting the same carry. All carry will be generated simultaneously with the exactly equal gate delay. And this is your final circuit. Here is the logic which this logic fits here. This particular logic which have input P2, G2, P1, G1, P0, G0, C0, and the output is C3, C2, C1. This is the whole circuit, carry look ahead generator, and this is your external circuit where we are generating P3, G3. P3 is A3 XOR B3, and G3 is A3 and A3 and B3. So in this way, when we design our circuit in such a way with the help of carry look ahead adder logic, then we are getting the sum and carry exactly after equal number of gate delay, and there will be no anonymous output change at the output when we are changing the inputs. So this is the way how we get an equal and exact output without any gate delay and without any anonymous change. So I think we should stop our lecture today here. If you have any difficulty, you can write to me, and I'll be continue sharing you the video lectures so that you can your doubts can be resolved.